Hello everyone. Today, let's clear up the confusion between stress and pressure. These are two fundamental concepts in engineering, physics and material science. Although they seem similar, they play very different roles in designing safe and efficient structures in the vehicles and machines. Let us break it down. What is pressure? Pressure is the force applied uniformly over a surface area. The formula is P is equal to F by A. P is pressure in pascals, F is equal to force applied in newtons, A is equal to area over which the force is distributed, maybe in meter square. Think of a car tire. The air inside pushes against the inner walls, creating pressure that keeps the tire inflated. If the pressure is too high, the tire may burst. If too low, it deflates, affecting the ride quality. Another simple example is pressing your hand against a table. The force spreads out over your palm, creating pressure. Now, what is stress? Stress is the internal resistance a material develops when an external force is applied. The formula is stress, which is sigma is equal to F by A, where sigma is equal to stress in pascals, F is equal to applied force in newtons, A is equal to this cross-sectional area of the material, maybe in meter square. Imagine pulling a rubber band. It stretches due to stress. If you pull too hard, it snaps. In engineering, materials are designed to handle stress within safe limits. Another example is tightening a bolt. If the stress exceeds the material's limit, the bolt may break. Right? Now let us see this formula-based explanations of their differences. Although the formulas for stress and pressure looks quite similar, there is a fundamental difference in how they apply. Pressure is equal to force by surface area, which acts externally on a surface. Stress is equal to force by cross-sectional area, meaning this acts internally within a material. Think of a car tire again. The air inside exerts pressure on the inner wall. This is external action. The rubber material experiences the stress as it resists the expansion force, which is an internal reaction. This difference is why engineers consider pressure in fluid systems like pneumatics and hydraulics, while stress is analyzed in solid materials like bridges, beams, and machine parts. The key difference between stress and pressure is, to simplify it, pressure acts externally on a surface. For example, air in a car tire, water pressure in a pipeline. Stress acts internally within a material. Example, a stretched rubber band, a loaded beam in a bridge. Pressure is uniform, while stress varies based on material strength and force applications. There are multiple types of stress and pressure. Both the stress and pressure comes in different forms. Normal stress acts perpendicular to the surface. Example, the car chassis under a load. Shear stress acts parallel to the surface. Example, cutting forces in the machining. Tensile and comprehensive stress, the stretching or squeezing forces. Example, suspension cables versus bridge pillars. Static pressure, this constant force over time. Example, this fluid pressure in a pipeline. Dynamic pressure, this changes with velocity. Example, airflow over a car body for aerodynamics. There are multiple real-world applications for both stress and pressure. These principles are used in automotive industry while we design engine components that should withstand combustion pressure. On aerospace industries, for example, ensuring airplane fuselage handles air pressure changes. On civil engineering, calculating stress on bridges and skyscrapers. On manufacturing in general, while designing the bolts, gears, and fasteners to handle loads safely. And these are some of the understanding one should have when and why the stress and pressure is important. Knowing these differences helps engineers in preventing material failure by designing parts within the stress limits, optimize pressure control in hydraulic and pneumatic systems, ensure safety in structures, machines, and vehicles. And that stress versus pressure explained, whether it's a car tire, an aeroplane, or a suspension bridge, these concepts play a very crucial role in engineering. Thanks for watching and stay tuned for more engineering insights.